All right, welcome. My name is Dan Galpin, and we're going to be talking about garbage today. I hope everyone is really excited to hear about garbage. A little bit about me. I have spent the last over 5 years as a developer advocate on the Android team, mostly working with game developers, which is why I end up dealing with so many low-level things, but also doing a couple of fun things you might have seen. I'm really proud of the work we've done with Udacity. I worked on both the Android Fundamentals class, Introduction to Android, as well as the Advanced Android class. And I have had no sleep. Literally, I have not slept in about 2 days. So this should be exciting. I think I'm funny. So I had a confession to make. If you looked at the description of this talk, when Ian Nee Lewis, who you notice is not here, and I started planning this talk, we were thinking like ocean liner big. And we wanted to cover all sorts of things. We wanted to cover binder and art and the OAT format, services whose names end in flinger, you name it. But a few weeks ago, we realized two things. First, there was no way we had time for all that. Even if we could write a talk that would cover all of that, we still couldn't deliver it in 40 minutes. Secondly, there were always a series of books and talks called Android Internals that covered lots of what we were planning. So we decided to focus the talk. So instead, I'm going to talk about one of the journeys that we've taken through the internals of Android. I should also mention that I did not write large chunks of this talk. Ian Nee Lewis, my cohort, did, but he couldn't be here today. I am, however, responsible for all of the slides. He wrote a script that I'm going to read word for word because I will forever stand in utter awe of his technical brilliance. And because I haven't slept in about a week. So let's get started. The great thing about spelunking through the bowels of Android is that pretty much anyone can do it. It's the beauty of open source. And you might think that since I work for Google, I have some kind of special advantage when it comes to understanding Android. I mean, anytime I want to, I can walk over and talk directly to one of the amazing people that actually wrote the system. And it is pretty awesome, but not only do I try to avoid doing that, more than I have to, the knowledge is actually pretty much spread out over lots of people these days. So while the Android engineering team is amazing, and I'm honestly really fortunate to be working with them, when I really want to know how something works, I'll at least first get into some code and try to find out for myself. So today, I'm going to tell you a story about how Ian and I journeyed deep into the Android runtime and found out something for ourselves. Specifically, it's a story of how we found out why you have to be careful not to waste too much time when trying to avoid allocations, especially when you're running on art. And we're actually going to show you how we did it. This particular story begins with a deck of cards, which is exceptionally appropriate since it also ends with cards. Now, Ian was writing a demo that drew playing cards. It was supposed to be an experiment about overdraw, but that actually turned out to be the least interesting part of the demo. Now, card games are a great test for overdraw because stacks of them have a lot of overlapping objects, but none of them are transparent like these ones are. So there's a huge difference between the number of pixels you draw in the worst case versus the number you draw in the best case. But to get that best case performance, you have to figure out exactly which parts of the card are visible. Now, there's a general algorithm for doing that, but it requires a lot of bookkeeping because it involves splitting rectangles into some unknown number of smaller rectangles. Now, the thing you need to understand about Ian, who was doing this, is that he is a C++ programmer. More than that, he's a game programmer. And a game written in C++, this problem would be the perfect candidate for some kind of object pool. So he decided to keep all of the rectangles in a simple pool. Now, how many people out there have actually used simple pool in their coding? It's part of the support library. I don't think he expected the object pool to make a huge performance difference, but he thought it might help a little. What surprised us both was that it didn't help at all. Instead, it totally tanked. I mean, the performance was absolutely abysmal. And so we decided to look for answers. We started where most people start when they have a performance problem, with the sampling method profiler and traceview. How many of you have used traceview out there? Come on, show of hands. Oh, that's good. You're listening. That's awesome. The profiler isn't as good as systrace at catching intermittent performance spikes, but it's really great at giving a big picture view of what's expensive and what isn't. And here we are. The culprit is simple pool release. Now, here's what that code looks like. That is in pool line looks kind of suspicious. Sounds like it might be a linear search. And of course, if we look back at our traceview output, we also see that is in pool there is right at the top of our list. So clearly it's costly, and it actually does do a linear search. It goes to check everything in the array to see if it's already in the pool. So if you have a really big pool, it's actually really expensive, especially since array access is not particularly cheap. So we decided to make an even simpler pool. Well, that was easy. We'll just make our own pool with a cabana, a waterfall, a diving board. I mean with unchecked releases. Very easy to get those mixed up. We're living on the edge. And of course, trace view output looks like this. It fixes our performance problems. Yes, it turns out you should be really careful when using simple pool. That linear search really makes large pools slow. We could pack up and go home now, but now we've got some code to play with. So we decided to find out how big of a deal is allocation in art anyway. I mean, so we did some crazy tests, like allocating thousands and thousands of objects in OnDraw. And we found that in most cases, unless the object was really expensive to create, like a paint object, it didn't really affect our frame rate. And we're like, what? I mean, no, we didn't just suddenly find out that allocations are free. All that stuff Colt McCandless told you is still true. What this experience taught us was that we didn't understand how allocations affected performance quite as well as we thought we did. And when you start seeing performance numbers that you don't expect, it's a perfect time to start digging into the code. So off to the debugger. I know what you're thinking. I love reading through code as much as the next crazy person, but sometimes you just got to step through it to understand it. Now, there's a lot of ways to debug the Android runtime. Some are easy and some are hard, and let's make things easy on ourselves. First, and this is going to shock you, we're actually going to debug an emulator build, okay? Now, how many of you actually use the emulator when you're writing Android software? Okay. Well, so devices are kind of finicky, so are network connections and USB cables. We're actually going to be doing a lot of native debugging. And unless you're trying to debug an issue with hardware code generation, there's really not a big difference these days between debugging against the emulator and a real device. In addition, when you're running on the emulator, you get to run as a root. And our images also include a version of GDB server. So you've got super, super reliable debugging, believe it or not, if you need to do native debugging on Android. Second, we get to avoid using ADB, which is really cool. Why? Because ADB was designed to be cheap, slow, and reliable, and it really manages to achieve two of those goals. Now, ADB is okay if you're using the GDB command line, which I know some of you are totally into. So if you're one of those people, just go back to your Emacs or whatever for a minute or two while I talk to everyone else. When I'm stepping through unknown code, I really prefer to use some kind of GUI. Now, Ian is a huge fan of Qt Creator because it's free and because it's not Eclipse. But ADB can't handle the amount of GDB traffic that an IDE like that generates. It works for a while, but at some point it just decides to quit. But fortunately, the emulator has its own IP port redirector that doesn't rely on ADB. And my experience with that is that it's really, really solid. Third, download the AOSP code base and build your own emulator image. Now, you don't have to do this, but it's so totally worth it. For one thing, you don't have to worry about your sources, symbols, and binaries being in sync. For another thing, and this is really important for this particular quest, you can actually disable optimizations on modules you want to debug, which makes stepping through the code a lot easier. Now, once you have a rock-solid debugger attached to the runtime, it's kind of addictive. I mean, you're seeing Android from a completely new angle. It's like you've been poking around a cave with a candle, and someone just gave you this high-powered flashlight. And if you're running a Windows box, building Android is a good excuse to install Linux VM. All right, let's start with my favorite piece of code, the bytecode interpreter. Now, there are actually two different implementations depending on how you compile it. One is a go-to table implementation, which is one of those pieces of code that simultaneously proves why C macros are horrible and why they're never going to go away. But fortunately, if you set the right compiler options, you get the implementation in interpreter switch impl.cc, which looks exactly like you always thought it would. Just one giant switch statement with a case for each opcode. If you've been struggling to figure out what's going on in the interpreter, just seeing this enough is to make you cry. It doesn't see as much traffic as it used to because of all the ahead of time compiling, but if you turn that off, this piece of code becomes the Rick's Cafe Americain of switch statements. Everybody comes here, which makes it the perfect place to set some breakpoints and learn how the runtime works. Now, since we're trying to minimize our allocation costs, maybe we should start by looking at how object allocation actually happens. Now, all object allocation starts at the same place in this interpreter, which is this new instance Dalvik opcode. But as soon as we get into the implementation of that opcode, things get a little abstract. So it turns out that the ART memory system is massively polymorphic. There are actually 8 different kinds of allocators that might be returned from getCurrentAllocator. Now, this is one of those points where it's really great to be stepping through in the debugger instead of just reading the code, because we can see exactly what we're getting, which is ROSALLOC. I mean, not always, but usually. And ROS stands for run of slots, which is basically a fancy pants way of saying fixed-sized block allocator. The slot is a fixed-sized block. The run is an array of those blocks. And the allocator owns a set of runs. Now, each run has a different slot size, so it can hold object of that size or smaller. And unlike my diagram, the number of slots in each run is actually calculated to make the run end as close to a page boundary as possible. Now, this is an awesome allocator. It's not the most efficient as far as memory usage, but it's got 2 really nice advantages. One is that it's practically immune to fragmentation. Second, bookkeeping is really easy. You never need to split or coalesce blocks, and you don't need to store the size of each allocation because the address of the allocation tells you everything you need to know. So even though you waste a little space at the end of any object that's not exactly the size of its slot, you get some of that back by not having to store any extra cruft alongside it in the heap. So not to mention that it avoids data alignment problems if you happen to have any of those. There's one really interesting way that ROSALLOC is different from the allocators you see in things like game programming. Because game programmers tend to use a stack to keep track of free elements. Now, you can implement that in a little array of bytes or shorts that has the same number of elements as there are slots in the run, and it lets you do both allocations and deallocations in constant time. ROSALLOC, on the other hand, tracks free slots in a bitmap. To allocate, you actually have to look through the bitmap until you find a 0. Now, technically, that's an ON operation. And when I first looked at this, I thought it was kind of weird. And then I thought it was kind of interesting. And then I realized it was freaking brilliant, OK? And here's why. First off, yes, the allocation is order n. But remember, these are actually fairly small little groups you're allocating from. So it's n times a very small constant. Furthermore, most CPUs can find the first cleared bit in a word on a single instruction. So the worst case allocation cost is just the number of slots divided by the number of bits in a machine word. On Android, we actually negate the bitmap word and then use something called _built-in _FFS to find the index of the first non-set bit. So we actually use a compiler intrinsic for that. And that's not even the brilliant part, though, because the brilliant part is what happens on deallocation. Because allocation in a multi-threaded environment is a huge pain. The best way to make it fast is to remove the concurrency. Just give each thread its own separate allocator, make a rule that memory has to be freed on the same thread that allocated it. But that really sucks for garbage collection, because part of the appeal is that you can do a lot of the work on a background thread. After all, we all have multi-core systems. We tend to have a core free that's not doing a lot. And what you get with ROSALLOC is almost the best of both worlds. See, there's actually multiple bitmaps for every run. One tracks which slots are in use, like I talked about earlier, but another one tracks slots that have been freed by a different thread. So instead of synchronizing the free list on every deallocation, you can wait until it's convenient and apply all pending deallocations by just NANDing the 2 bitmaps. By the way, I'm showing a lot of source code here, and it's a little small, so I apologize in the middle of this. Once again, though, this is fracking brilliant, because you can now have, and yes, you can have thread local runs, and the locks are sharded by slot size so that even shared runs have way lower contention. There's a bunch of other cool stuff in ROSALLOC, but we should probably move on before everyone starts calling me the crazy ROSALLOC guy. So the really sad thing is that it's hard to implement. Well, you really can't implement anything this elegant in Java. You'd end up reinventing the entire reference system, and it'd be kind of a maintenance nightmare. So yeah, allocating from our object pool isn't a whole lot faster than allocating from the normal Java heap, and it's way more work. But we kind of expected that. I mean, no one ever explains about the cost of allocation in a garbage collected runtime. It's always about the cost of collection. So the question is, why aren't we seeing these massive collection pauses when we allocated massive numbers of short-lived objects? Now, Rosalind gave us a little bit of a clue. They didn't spend all that effort on concurrency for nothing. It's not that the garbage collector is doing nothing. It's that a lot of its work is being done somewhere else other than the main thread, and it's still work, and we'd like to minimize it, but it's not causing the jank that it did on Dalvik. So there's one piece left in this puzzle, and it has to do with how the GC manages to do so much of its work on a background thread. Now, actually, since we spent so much time talking about how great the allocator is at concurrency, it's probably worth going over why this is even a problem. Now, the GC has to figure out which objects are live and which are dead. And it does this by starting with the object on the stack and following their references all the way down till there are no more references left to follow. Every object that got visited during that procedure must be live, because clearly there's a chain of references that your application could follow to access that object. Every object that gets left out is dead, or at least it's not live. Now, the GC guys tell me that's a little bit of an oversimplification, but it's a good first approximation. Thing is, this process is not lightning fast, and if it's done concurrently, then your application is busy connecting and disconnecting and reconnecting references while the GC is trying to trace them. So let's say that object A has a reference to object B, and object C has a reference type that's currently null. Now, for whatever reason, the GC visits object C before it visits object A. Following me? Okay. Now, let's say that after the GC has visited C, but before it visits A, you give object B to object C and null out A's reference. For all the GC can tell, A and C both have a null reference, and it never even saw B. So the question is, how do you fix this? And it turns out the answer to that question tells us a lot about how we can shoot ourselves in the foot by trying to outsmart the garbage collector. And it takes us back to the subject of cards. If you take another look at the glorious switch statement that is at the heart of the Dalvik interpreter, you'll notice that a lot of opcodes have an extra call in them. And this call to check suspend is a checkpoint. It's a place where the thread checks to see if the GC wants it to do anything. Among other things, this check lets the GC tell the thread to stop completely, which is what it has to do if it wants to get an accurate count of which objects are dead and which ones are alive. And this is called the GC pause. Now, clearly, one way to make sure the GC gets an accurate count is just to visit the objects all over again, but that would be a colossal waste of time. I mean, that would be like a cupcake move. So instead, how about how we just revisit the objects that got changed while we were busy doing our first pass on the object graph? Now you're talking. That's some gingerbread level thinking, my friends. So how do we tell what's changed? Let's go back to that switch statement one last time. Now, you probably haven't noticed this, but there's actually a specific set of opcodes just for moving references. And that might strike you as being odd, because references are just 4-byte binary values, same as integers. Why not just reuse the existing integer moving opcodes? And this one takes a little bit more digging, because the answer is actually several layers down in the call stack, underneath some templates and macros and some random cruft. But eventually you get at this thing called write barrier field. Now, the word barrier is a little overloaded in computer science. Here it means something that the runtime has to do before writing to a reference field. There's also the concept of a read barrier, but it's really not that important to this particular discussion. Anyway, take a look at what write barrier field does. It calls mark card. See? I told you there'd be cards. All right. In this case, a card is just an area of memory. It's kind of like a page, only it's not the same size. And besides, that word was taken, so we call it a card. Now, marking the card just says, hey, something in this memory has changed. Now, why do we even have cards? And it's really for the same reason we have pages. So we can have metadata about memory that takes up less room than the memory we're describing. So for pages, we keep data like whether it's read-only or executable or any of that other mprotect stuff. For cards, it's pretty much just dirty or clean. It's just a write, if you look at the source code. It's not even an atomic. which, by the way, we can get away with because there's no read, modify, write. In a concurrent environment, it's just a write, and the read is done during the GC pause where the value can't change. So what's so important about the card table? Given the information in the cards, the GC doesn't have to rescan every single object during the pause. It can focus its attention on the objects that might be dirty. Now, this idea extends far beyond just finding the objects that change in the last concurrent scan, by the way. There are plenty of objects that almost never change. For instance, class objects. If we can, we want to avoid scanning those objects ever. And we can get away with that because if for some reason those objects ever do change, their cards will be marked. Now, the card ID isn't perfect. For instance, if a card happens to contain more than one object, there's no way to tell which object is dirty. All of them have to be rescanned. Even worse, an array of objects count as one object when it comes to card marking. That's one object with a whole lot of references, which means if you insert or remove an object from an array, the entire array gets rescanned. So now we come full circle, because our pool of card rectangles might actually end up as a victim of card marking. I know there's a country song in there somewhere. But it's only one of several factors that make allocations cheaper on art. And I wish I had actually more slides to talk through the rest of them, but I'll talk about a few of them. One of them is better collection pass scheduling. Now, art in general tends to do a better job of figuring out when to run collection passes, which means that GC for alloc is a thing of the past. And two, it keeps a list of objects that have been allocated since the last GC. So when you add that information to the card table, art gets the ability to collect super short-lived objects without even triggering a GC pause. And that's why allocating ludicrous numbers of simple objects doesn't kill art the way it did Dalvik. And two, oh, sorry, I already said this. So finally, let me in conclusion, because this is going to be really short, guys. So don't walk out of here and tell your friends that allocations don't matter anymore. First of all, we don't want to incur the wrath of Colt. And besides, the point of this talk isn't necessarily just to add to your stock of pro tips, but hopefully it's to give you a little bit of understanding of how things are working inside of Android and how you can do and enjoy going through Android yourself. So I hope I've given you some of the tools and encouragement you need to go on your own adventures to the Android code base. I mean, after all, what else is open source for if we can't learn from it? So we're looking forward to hearing your stories. If you want to contact me, that's where I can be found. And thank you all, and you all get 20 minutes back or so. So enjoy the rest of your time here at the barbecue. And if you have any questions, I am more than happy to take them now.